In this video, I will show you how to find the resultant vector when two or more vectors are acting together. Now the key is organization. Bam! Use this chart and use it well. Pilot Amelia Earhart's flight plan has her leaving San Francisco International Airport and flying a Boeing 727 due east. There is a 65 mile per hour wind with bearing 60 degrees. Find the compass heading or bearing Earhart should follow and determine what the airplane's ground speed will be, assuming that the speed with no wind is 450 miles per hour. So there are two vectors to consider: the velocity of the plane and the velocity of the wind. The resultant vector is what we're looking for, because that will be the actual ground speed and direction that the plane will move. The first row of this chart is for recording the magnitude and direction of each vector. When we do the direction on this chart, it has to be measured from the positive x-axis going counterclockwise. The second row is where we will convert magnitude and direction into component form, x and y, horizontal and vertical components. So let's see. Let's start by recording the magnitude and direction for each of the two vectors, for the plane and the wind. Now they mentioned that the plane speed is 450 miles per hour. So that is the magnitude of the plane velocity, 450 miles per hour. So we just need to go back and find the direction. But for now, let's switch over to the wind. It's a 65 mile per hour wind. That's the magnitude of the wind velocity, 65 miles per hour. Now, what about direction? What do they say about the direction of the plane? Well, the plane is flying due east. Okay, and what about the wind? The bearing of the wind is 60 degrees. So bearing 60 degrees. So for the chart, we need to convert each of these directions into an angle measured from the positive x-axis. However, if we're talking about due east, which is how the plane is flying, well, that is the positive x-axis. So that is 0 degrees. So that's what we need to put on the chart for the plane's direction. It is 0 degrees. Now, how about this bearing of 60 degrees? A bearing of 60 degrees means 60 degrees measured clockwise from north. So we're talking about a vector that's here if this angle is 60 degrees. But what we need is the angle measured counterclockwise from the positive x-axis. So this would be 30 degrees. All right, they have to add up to 90. So 30 degrees is actually the angle that we will use on the chart. Now, if only there was a way to directly combine magnitude and direction to get a resultant vector. But sadly, there is not. That's why we must convert these into component form, x and y, horizontal and vertical. Now, what's going on with the plane here is a special case when we think about component form. The plane is traveling due east. That means there is only a horizontal component. There is no vertical component. So what was the speed? 450? All 450, that is the horizontal component. The entire vector is horizontal. And I'll make sure it's positive because it's going to the east. If it had been going to the west, it would have been a negative 450. I will put simply 0 for the vertical component because there is no vertical component. On the other hand, when I do the wind velocity, when I convert this to component form, what I will have to do for the horizontal component, I will do r cosine theta. That will give me the horizontal component. If I do r sine theta, that will give me the vertical component. So that's what I'm going to have to do for the wind. So r cosine theta would be 65 cosine 30. Whoops. And r sine theta will be 65 sine 30. Just run this through your calculator. The horizontal component is 56.29, while the vertical component is 32.5. And we'll just record that on the chart right here. So now that we have both vectors written in component form, we can find the resultant by adding these vectors together. We'll just add the horizontal with the horizontal and the vertical with the vertical. So the resultant vector has a horizontal component 506.29 and vertical component 32.5. But what we need is magnitude and direction. So let's slide off to the side and calculate the magnitude. We can easily find the magnitude by using the magnitude formula. We will do 506.29 squared plus 32.5 squared, and we'll do the square root of all that in the calculator. So 507.33. So that is the actual ground speed of the plane, which we will record here, 507.33 miles per hour. All right, that's the speed of the plane with the wind blowing on it. We also need the direction. So let's get ready to calculate the direction. Okay, what quadrant will we be in? We have this horizontal component that's positive, and we have a positive vertical component. So that means we're to the right and up on this graph. We are in the first quadrant. So go ahead and draw a vector in the first quadrant, and then begin to contemplate the vertical and horizontal components. Okay, 506.29, that's the horizontal. 32.5, that's the vertical. All right, obviously this drawing is not to scale. We can use this drawing to find the reference angle R, because the tangent of this reference angle should be 32.5 over 506.29. So the angle itself should be the inverse tangent of the fraction. Calculator. So this reference angle is 3.67 degrees. However, this is not the direction that we will put on the chart, even though this is actually the direction as measured from the positive x-axis, which isn't always the case, because for our final answer, we always need to record our direction using the same direction style that was given to us in the original problem. So, bearing. In the original problem, all the directions were given in terms of bearing 60 degrees. So we need to somehow convert this into bearing. So remember that bearing is measured starting at north and moving clockwise. So this is the bearing that we need to find. And well, these are going to be complementary. They're sitting here inside of this quadrant, 90 degrees. So all we really need to do is subtract from 90. And that'll give us the bearing. So the bearing is 86.33 degrees, and that's what we put on the chart. Now it's crucial that you actually use the word bearing. If you just say 86.33 degrees, that would mean that you are measuring starting from the positive x-axis and going counterclockwise, which is not what you want. Let's go ahead and put a box around it because that is the final answer. Let's go ahead and do one more problem. Now this one is pretty similar to the last one, so I encourage you to pause the video and try to do this problem by yourself. Now as always, the key is going to be organization, so get used to using this chart. A plane flies 30 miles on a bearing of 200 degrees and then turns and flies 40 miles on a bearing of 10 degrees. Find the resultant displacement vector as a distance and bearing. This is a displacement vector problem where the first vector represents a distance and direction that's traveled by the plane, and then the second vector represents sort of another part of the trip in a different direction and for a different length, and then the resultant vector represents the overall journey of this plane from beginning to end. So it's sort of like we have trip 1 is a vector, all right, a certain length and direction, and then we have this other vector which we could call trip 2. And then of course the resultant vectors is what we will be looking for. So go ahead and set up your table like this, and for the first row we will record the magnitude and direction for each one of these displacement vectors. When we do the direction, we will have to measure from the positive x-axis counterclockwise. In the second row we will record the component form for each vector, the horizontal and vertical components. So let's see. The plane flies 30 miles on a bearing of 200 degrees. The 30 miles is the magnitude. So 30 miles. And then we've got this bearing 200. I'm going to have to come back to that. Bearing 200. Okay. Then the plane turns and flies 40 miles. Okay, so that'll be the magnitude of trip 2. Will be 40 miles. And then we'll need the direction, which we will get from the bearing of 10 degrees. But for right now, I'll just write that down. Bearing 10 degrees. All right, so the reason why I didn't write the direction down yet is because we need to convert this bearing into a direction that is measured starting from the positive x-axis and going counterclockwise. So a bearing of 200 means start here at north and start going clockwise. So far I've gone 90 degrees. If I went to here, that would be 180 degrees. If I went all the way to west, that would be 270 degrees. That would be too far. So I'm going to stop here in the third quadrant. So my vector is in the third quadrant. So this is the 200 degree bearing that we're given. Now, what we need is the direction as measured counterclockwise from the positive x-axis like this. It would be helpful to know the reference angle that is right here. Okay, what is this reference angle? So remember, the vector itself is at 200 degrees bearing. If I had kept going to the west, that would be 270 degrees. So this reference angle is the difference between 270 and 200. In other words, 70 degrees. So knowing that the reference angle is 70 degrees, it should be easy to figure out what this blue angle is. Let's call it theta. Theta should equal 180 degrees plus the reference angle of 70 degrees. Because if you look at this blue angle, it goes 180 degrees as we arrive at west, and then an extra 70 degrees. So the 250 degree angle is what we will record on the chart. So the bearing of 200 is the same thing as 250 degrees measured from the east. Alright, let's do the same thing with trip 2. Alright, we have the magnitude, we need the direction. They gave us a bearing of 10 degrees. That means starting at north, you move 10 degrees clockwise. So this vector is in the first quadrant, and this is the 10 degrees right there. For the chart, what we need is this angle that's measured from the positive x-axis. This is really simple because these are complementary. If this is 10 degrees, this must be 80 degrees. They have to add up to 90. So the 80 degrees is what we will put on the chart for the direction of trip 2. Now there's no way to directly combine the magnitude and direction of these two trips to get the resultant vector for the whole trip. So what we need to do is convert them both into component form. And the way you can convert from magnitude and direction to component form is if you do r cosine theta, that gives you the horizontal component. And if you do r sine theta, that will give you the vertical component. So that is what I'm going to do. For trip 1, r cosine theta would be 30 cosine 250. R sine theta would be 30 sine 250. Calculator. So the horizontal component is negative 10.26 and the vertical component is negative 28.19. And we'll just record that on the chart right here. Now let's slide over and do the same thing for trip 2. R cosine theta would be 40 cosine 80. And r sine theta will be 40 sine 80. Back to the calculator. So the horizontal component is 6.95 and the vertical component is 39.39. And we'll just record that here on the chart. Now that we have component form, we can simply add these two vectors together, trip 1 and trip 2, and that will give us the resultant vector, the displacement of the overall trip. So we'll just add the horizontal component with the horizontal and the vertical with the vertical. So the resultant displacement is negative 3.31 comma 11.20. So that's component form, but we really need magnitude and direction. So let's calculate that off to the side. Let's start with magnitude, which we can easily calculate using the magnitude formula. So we will do negative 3.31 squared plus 11.20 squared, and we'll just do the square root of all that in the calculator. So the magnitude is 11.68, which means that the overall distance traveled from the beginning of the trip to the end of the trip is 11.68 miles. Now we need the overall direction of the trip. So we need to take this component form and convert this into a direction. The horizontal component is negative, the vertical component is positive. That means we are west and north. So our vector is in the second quadrant. So let's go ahead and draw a vector into the second quadrant. And then let us contemplate the vertical and horizontal components. So the horizontal component here is negative 3.31. The vertical component is the 11.20. This puts us into a position where we can find the reference angle R. And hey, we're finding direction. I forgot to label what I'm doing. So we found magnitude, and now we're finding direction. All right, always best to stay organized. So the tangent of this reference angle R should be 11.20 over 3.31. Notice that I am ignoring this negative sign because I really just want the positive value of this angle R. So the measure of angle R should equal the inverse tangent of this fraction. Calculator. So the reference angle is 73.54 degrees. Now normally what I would do is I would figure out what is the angle theta measured from the positive x-axis, which would be 180 minus the 73.54. However, in your final answer, you have to make sure you are giving the direction in the same form that it was given to you in the original problem. So in the original problem, they gave us direction in the form of a bearing. So in our final answer, we need to give the direction as a bearing instead of an angle measured like this from the positive x-axis. So remember that bearing is measured starting at north and moving clockwise. So if we start at north and move clockwise like this until we get all the way around to the vector position, this is what we need to actually find. This is the bearing. So let's see. As we move from the north and rotate around, at east that's 90 degrees. At south that's 180 degrees. At west that's 270 degree bearing. So the bearing of this final direction should be 270 degrees plus this extra reference angle of 73.54 degrees. So the bearing is 343.54 degrees, and that is what we will record on the chart for the final answer. So bearing 343.54 degrees. All right, and we'll just go ahead and put a box around this because this is the final answer. One more thing. Make sure you use the word bearing when you write down a bearing. If you just said 343.54 degrees without saying the word bearing, that would mean that you were measuring from the positive x-axis counterclockwise instead of measuring from the north going clockwise, which is what bearing is.